Good morning. So it's fourth lecture, and today we will be discussing composite systems. So previously we discussed a single quantum system with its own Hilbert space and its states in that Hilbert space. Today we will be discussing a system that that consists of at least two systems, two different subsystems, and it's the simplest possible example is probably two two-state systems. So instead of one two-state system, we have two-state systems. So now the interesting things I'll talk about in this lecture. Uh, uh, the main interesting thing will be entanglement. Yes, but let's start how we describe such a system. So suppose we have a 1-2 level system and its states are let's say 1 and 2. Let's label with 1 and 2. And we discussed that the state of this system in general can be a superposition of these two. So it's like alpha 1 plus beta 2. Now if we have two such systems, the state, what could be the state of this composite system? That's the question. So first thing that comes in your mind would be, maybe we have another copy of this system and it has its own 1 and 2 states, and we can label them with the A and B, or maybe 1 prime and 2 prime. So let's use A and B. So and its states can also be, let's use the same symbol here. So and maybe we can use the same alpha beta, but let's use gamma and delta. Now what's possible for the composite system? Well, it seems easy. We can simply, let's call that state phi for system A and B. So system A can be any state in this form, and system B can be in that form. So let's put A here, and let's write it like this. So system A can be in some state. It can be superposition of its own Hilbert space, and system B similarly. So this is one form, and what we can do is we can just multiply them and see that it becomes alpha, gamma, and 1 1. And now let's skip these A and B, and the first number here will correspond to A and the second will correspond to B. So that can be taken as a convention. And okay, thank you. So if we multiply them, then from these two terms we get this, and then we get alpha and delta, and this is 1 2, and then beta gamma 2 1 plus beta delta 2 2. Okay, so this seems plausible, but can we do more than this? So can you think of anything other than this for this system, so as a state? So can this system, this composite system, can have states, I mean, that cannot be written in this form, that are not simply a product of this form, that's something else? Can we have that? So sorry, no, I'm just talking about the form of the state at the moment, yeah, not the reason why you can get that. So basically, let me rephrase the question. And so a state of a system lives in its Hilbert space. Okay, so for one two-level system, its Hilbert space is spanned by these two cats, and in general a state can be written like this, and similarly for the second two-level system. And now we have a composite system where we have two-level systems. So we should be talking about its Hilbert space, basically the state space of this composite two-level system. And then any vector in that space would be a legitimate state for this composite system. So at the moment I use my intuition and form this kind of state that would have this form, but can this system allow a state that has a different form? So basically, is the Hilbert space bigger than states spanned by this form? So, well, we can, I mean, we cannot.
All possible states are covered.
No,
all
sir.
Possible.
No, sir.
You want to, I know, break it into entangled and non-entangled states.
Yes.
But everything is covered here. This is the most general form.
No, sir. This is not the most general, because we have these two numbers here. So these two numbers, they need to obey a certain relation because of this form.
Alpha
So
squared
here
plus
alpha
beta
square,
squared is 1 and
yes,
gamma squared plus delta
yes.
squared.
But in general, the state could have been written with any general A, B, C, and D. And if we start with this form, with alpha, beta, and gamma, delta that obey certain restrictions, then we cannot write any general A, B, C, D from these products. It looks like that, but that's the whole point actually. So let's start with the Hilbert space of this composite system. So instead of making these kind of states, so this is Hilbert space of first two-level system, this is the Hilbert space of second two-level system, and what we do is we make these kind of products for these basis states. Okay, so the Hilbert space of this composite system will have 1, 1 as one basis state, 1, 2, basically these 4, 2, 1, and 2, 2. So now any state in space spanned by these 4 will be a state for the this composite system. So in general, let's call it psi. We can have like A 1, 1 plus B 1, 2 plus C 2, 1 plus D 2, 2. Okay, so that's the most general form. But what's the difference between these two? So in this case, if we have this form, so we started from this, so of course it has this product form. Okay, but for the most general case, it's not always possible to write that state in such kind of a product. Okay, so if you can suppose, if you have some state that where you can write this product, then you would call it a product state. Okay, that's simple. And if you can't write that as a product state, then you would call it an entangled state. So it would be an entangled state of these two level systems. Okay, that's the terminology. Okay, so
but there's a one-to-one correspondence. You see, A squared plus B squared plus C squared plus D squared equals 1. Here, the sum of those squares equals 1. And can't you solve?
okay, so a normalization would put this restriction here, and normalization would put another restriction here. and it would be alpha gamma mod square plus alpha delta mod square plus beta gamma mod square plus beta delta mod square. That's fine, looks similar, but the problem is that these alpha, beta, and they also have these restrictions. So these set of parameters are more restricted actually than that. These parameters only have one restriction, so basically you get like suppose they are real, then you would get like 3, and if you assume them complex, then 2 plus 2 plus 2 plus 2, it would be like 8. 1 is fixed with this, so 7, and 1 may be a phase factor, so 6. So at least there would be like 6 parameter here.
So you're saying that if you know that, you can't, it's not a one-to-one correspondence.
Yes, so this is kind of a subset of those. In general नहीं कर सकते. So in some cases you can, and then you would get this form, of course, and then we will call it a product. Okay, so now you know that when we have a composite system, how to write its basis state and what's its Hilbert space. So Hilbert space is spanned by these product. Okay, so now to differentiate between this kind of state and that kind of state, what can we do? So there are certain things that we can do, and usually when we have a composite system, we don't always like to work with that full system. Usually we like to work with a part of that system, a subsystem. Okay, so that means instead of two-level system, we are actually interested in one two-level system, but somehow that two-level system is coupled to another two-level system and we can't get rid of that. And okay, so situation like that. So in this case, the density matrix formalism that we introduced last time, so how to write a density matrix, so that would be very helpful. And we can start with the density matrix of this composite system and then obtain density matrices of these subsystems. And since those density matrices are of the subsystems are only relevant to those subsystems, so we have a different name for them. So we call them reduced density matrix. Okay, so we start with density matrix of this system. So suppose this composite system is in this state and it has a density matrix, and then we'll calculate density matrices of subsystem, and then the density matrix matrices of those subsystems can tell us whether the state was a product or entangled. Okay, so that would be easier. And the reason why this is so important is that entangled states are kind of the building block of the whole quantum communication and quantum information sciences. Okay, so for those areas, what you need is entanglement between states of one system and with another system. Okay. So let's call this rho AB, and rho AB is besides that. So this is density operator, so it's written in operator form, but we usually don't worry about whether it's in the operator form or a matrix form. We usually refer to it as density operator or density matrix, okay, in loose language. So don't worry if I call this density matrix or call density matrix or density operator. Okay, so we can compute this and it's very easy. So we have like what we can do is there are 4 numbers here, so we will get 16 numbers. Okay, so should I calculate all those 16, or maybe calculate a few and then you would know. So okay, so let's start with this. So the first one, so A star A, so we would get this 1 1 and it's cat. So and it's dual, that's 1. That's diagonal because these two states are the same, so in matrix form it gives the diagonal matrix elements. Okay, so we call them diagonal. And then similarly for B square, C square and D square. Okay, so they would be like maybe instead of writing them like that, we can simplify the situation by maybe relabeling them as 1, 2, 3 and 4. Yes, that would make things a little easier. So and then there would be off diagonal elements, and with A star, for example, let's call it A, so that we have that. So with A 1, we can have now B, C or D. So B, and so on. With B, we will have A, C, D and etc. Okay, so we'll have 16 terms in total. And if we write them as matrix, these first 4 would be diagonal, and then A, B star. So here would be A, B star, A, C star, A, D star. Similarly, B, C star, B, D star, etc. and C, D star. And here you just need complex conjugates of these. Okay. Yes, so it's a Hermitian matrix. So rho dagger is equal to rho. So we can skip writing that. So it's this matrix, and if this were an isolated system, as it is actually, then we can always compute this quantity and see that. So we can compute this quantity and see that it is equal to the matrix itself. And for an isolated system like this, where we started with a cat for, so like this, so if density matrix is written using a cat as a projector like this, then this will always hold. So you can take any A, B, C and D as an example and compute this. Okay, so you'll see that it's actually this one. So here this is a matrix, and square means matrix time matrix itself using the matrix multiplication rules. Okay, so now what's special here? The special things We will see those special things when we compute the reduced density matrices of our subsystems. So how to do that? Okay, so reduced density matrix. So to compute these reduced density matrices of our subsystems, suppose we like to compute it for subsystem A. It's very simple. The operation is that what you do is you take a trace. So basically you sum the diagonal elements, but not in the usual sense. So if you take a trace, that would mean the sum of all these elements, but here this trace is very special trace. So it's called partial trace. So we write it like this, and what we do is we sum over the diagonal elements but of the other subsystem. So it's a partial trace over the states of B, and like this. So we compute partial trace over B of this density matrix to obtain the reduced density matrix for the rest of the states. And if we do the opposite, if we like to compute density matrix of row of B subsystem, then we would be computing partial trace of this. Now what's this partial trace? So now we have this matrix and that projector form as well. So let's start from this. The partial trace means that sum over the diagonal elements of B. So let me use this space here, and we can actually maybe here we can actually expand this and call those states whatever their name was, 1 and 2. Let's call them maybe some symbol, maybe sigma or something. So sigma is 1 2, so these are over B. Okay, so basically 1B and 2B states in the original product form, and you do that, and so this partial trace is basically this thing, that you sum the diagonal elements that are diagonal in the B. Okay, so if you write in this form, it's very easy to get this partial trace from here. So let me remind you that this 1 1 is basically 1 1. Maybe let me write it here. This was 1 2, I guess.
2 1 2.
Okay. So these are the states. But just notice these labels. So what we want is we want to focus on this part, B part. So if we have in the second part, we have in this project, in these projectors, we have the same second part, then we will sum that up. Okay, it's a little bit hard over here, I guess, because I didn't use this notation, but let me make a slight jump and maybe tell you the final.
If you had used Aij, and then you would sum over I from 1 to 2, J from 1 to 2, that would have been easier. Instead of if you had used A.
Oh,
I.
yes. Okay, yes, but I'm already worried about yes this notation. But well, let's start from this term. Maybe we do that term by term. So at the moment, make some space here, and then we'll come back here again. So the first term, does it contain anything diagonal in the B? So it's 1 1 is basically 1 1 1 1. With this is for composite system and this is for system A and B. Okay, so that should be clear, I guess. So is it diagonal in the states of B subsystem? Yes. So see here. Yes. So it's 1 1 in here and in here. So it's diagonal. So we note that we will include it in the sum. Now the second term 2 2 will also be diagonal because it will contain no, it's
1 2 2
okay, yes, 1 2
2
1 2.
Okay.
Yes, I'm calling this 2 here. I'm not sure if it's consistent with the previous, but so here again it's diagonal in the B. Okay, states of B. So we'll keep that, and all these diagonal terms will be diagonal in B as well. So this 3, because it's the same state over here and here, so it must be diagonal in B as well. Okay, now let's start with this 1 and 2. So it's basically 1 1 and 1 2. This 2 is 1 2. This is 1 1. That's the dictionary here. Okay. This is not diagonal in B. It's diagonal in A but not in B. So we can discard that. And similarly, we can check which terms are diagonal in B. So we keep all of them, and then we simply sum them up. Okay. So these inner products, they simply choose those diagonal. Okay, because it's the same B and B here, so they choose those diagonals. Whether it's 1 or 2, they choose them, and then you sum them up. But these projectors, these inner products, they are not simple numbers. Why? Because they are in a product only in the space of B, not in the space of A. So the thing that we obtain from this inner product would be an operator in the space of A. So it would be a matrix in space of A. Okay, because we are only taking in a product with B. So here, for example, if we sum them up, this term will give us one element of row A. This will also contribute to the same matrix element. This is not contributing, but let's see something else that has this 1 and 2. So this is 1, this is 2, so 1 and 3. So this term. So this term, it has like 1 1 and 2 1. It's diagonal in B, so it will contribute, but it's 1 2 matrix element of row A. So these terms, when they contribute, they can contribute to different matrix elements. So these two will contribute to row A 1 1, but this will contribute to row A
1 2
1 2. Okay, so when you do all this, so you obtain a 2 by 2 matrix with 4 matrix elements, and yes, so you will not leave any state of B because you have already taken trace over B. So you will get a 2 by 2 matrix for A. That would be reduced density matrix for A. Okay. So that's if you have these this form and you do that. But how to do this in a simpler way if you have this 4x4 density matrix of the full system? So that's actually much easier. So let's suppose this is row A, B. So it has these 4 numbers, whatever they are, don't need to name them at the moment. And all we need to know is the order of the basis states. So this 1, 2, 3, 4, which one is which? So it's 1, 1, 1, 2, 2, 1, 2, 2, and 1, 1, 1, 2, 2, 1, 2, 2. Okay. So now it's let's see, we can make these 2 blocks and then see that this block, it has this 1, 1, this is 1. So for subsystem A, this whole block is for its state 1, okay, and this is for its state 2. So yeah, so in this structure, so this is 1, this is 1, so this is for 1, and now for first state of system A, the second is the running state, so it's 1 and 2. So that's the structure here. So that means you can divide this in these 4 blocks, and then what you can do is, for taking partial trace over which one would be easier here. So if we like to take partial trace over second one, B subsystem, that's if we like to compute row A, what can we do is, here the second is 1, 1, 1, and here for the second it's 1, 1. So now this 1, 1 means this second one and this second one. So this is 1, 1 and this is 2, 2. So for second, so let me write it 1, 1 and 2, 2, and this 1, 1 and 2, 2 is for subsystem B. So these are diagonal elements of in this for B. Okay. Similarly, you can see this and this. So all that is changing here in different blocks is which component belongs, which component is for subsystem A. Okay, so this is 1, 1 for subsystem A. This is 1, 2 for subsystem A. So these blocks are for subsystem A. 1, 1, 1, 2, 2, 1, 2, 2, and then their diagonals, they are diagonal in the second. So to compute this trace over the second, it's very easy. You compute simple traces of these blocks. That means what you do is, you get 4 numbers out of these. So you sum them up, you get 1 number, you sum these up, you get another number, then another, then another. And doing this, you are discarding some information, and that information is over here in these matrix elements. So we are discarding that, but we still have enough information that would tell us correlation between A and B and etc. Okay? So this would be row A. So if you have a density matrix of a 2 levels of a composite system made up of 2 2-level systems, or 2 qubits or 2 spin halves, then you can do this and you get density matrix of A. Similarly, if you like to obtain density matrix of B, either you change the order of the bases and switch them with A and do the same, or you can simply now recognize how to do that. So if you like to obtain the diagonal in A, then these are the blocks. These blocks are diagonal in A. These diagonal blocks are diagonal in A, because this is 1, 1, this is 2, 2 for A. this is 1 2, this is 2 1 for A. Okay, that's what we have already used. So this is one block of A, but what's changing is the states of B. So this is 1 1 of B, 2 2 of B, 1 2 of B, 2 1 of B. Okay, so if we simply take these two blocks, this, and sum them up element by element. So we take these two, sum them up, and we get this 2 by 2 matrix, and this would be row B. Okay, so if you take partial trace over A, you simply take these diagonal blocks and sum them up, or overlap them and sum them up. And if you like to take partial trace over B, then you have to take all 4 blocks and sum their diagonal elements as usual, just like a simple trace. So here things are like simple trace for each block. Here we are not taking, I mean, in simple sense, we are not taking trace or anything. We are simply summing these 2 blocks, these 2 diagonal blocks. That would be partial trace over A. Okay, so this is very simple, and what we can do is we can take some specific state and compute its maybe density matrix, and then see what these two look like. So let's start with a state that has this product form. Okay, suppose we have for A, let's suppose we have this, and for B we can also have the same state. This is Hilbert space of A. We can have something like this, or maybe we take the other state with sign, with opposite sign, doesn't matter. If we take the same sign, things would be much easier, so let's do that so that we don't waste time, I mean, following the sign. So suppose we have our system A in this state, system B in this state, and our composite system in the product state of these two. So then how can we compute its density matrix? Well, let's first compute all these numbers, and it would be like 1 by 2. All these are 1 1, so it will, everything will be 1. Okay, so let's directly write it. So we can directly write it because it's very simple. So, or maybe let's make it more mathematical. Let's represent this state in terms of these two, and then it will be like this. It will be a column vector in that space, and similarly a column vector in this space, and then that product will be actually what we call tensor product. So you multiply each element of your first vector with the full vector. So the tensor product, this will be like 1 by 2, these numbers, and then 1 1 1 1. So you multiply this whole vector with this number, you get these two. You multiply this vector with this number, you get these two. If you choose the other sign, let's choose the other sign as well. If you choose this sign, then it will be like that. Okay. So now, how to compute the density matrix? Basically, you multiply this with itself, outer product. So let's assume we are dealing with the positive sign. So it will be 1 by 2. So 1 by 2 will be with this and its dual, so it will be like 1 by 4, and everything is 1. So this will be our density matrix. Now let's compute the reduced density matrix of say a system A.
You're just taking the plus or minuses.
Yeah, just plus, because for minus I'll have to be more careful, so I don't want to do that, because then there will be some mistakes.
So
and
the minuses should go away.
Okay.
And also.
Okay. Let's deal with the first one only. Okay. Okay. So now let's do this and see the structure. And row A, where we take partial trace over B, would be like this is 1 by 4. Let's take that. Take this trace for this block. So this is like 2. Trace for this block 2. And similarly is 2, 2, which will be take 2 common, and then it will be like 1, 1, 1, 1. And now, since they are exactly similar, so row B should be the same, but you can compute that. You take this block, sum it with this block, it will be 2. Okay, so it will also be 1, 1, 1, 1 with half. So these are our reduced estimates. Now what's,
just to clarify,
yeah,
you're taking an unentangled state.
yes,
And you're saying that row AB is row A tensor product row B.
yes, actually,
So that's actually the definition of
yes, product state,
unentangled.
yes, but I'm at the moment trying to kind of demonstrate how to compute these partial traces. So by taking a specific state, so if I use like ABC, it's very hard to imagine, but if you take like something like 1, 1, it's very easy to work with. Okay. So in this case, as per this subset, so this row B is actually row A times row B. So this is the symbol for this tensor product that we used to get from here to here, okay, or from here to here. So in this case,
And just to make me happier, can you put tensor product over there for psi? Psi is tensor product.
okay, yes. So you can also write it here. Okay, it looks more dangerous, but it means the same. So yeah, so if you have to write it with hand all the time, then you usually skip and you know what it means. I mean, it is a tensor product and things like that. But yes, for presentation it looks very good, Okay, so this is a tensor product and this is a tensor product in this case. Why? Because we chose this product state. So if you have this product state, you can already see it from here. If you compute its density matrix, row A has its own Hilbert space, it will multiply with its own dual, and that would be definition of this, and this will become the other part. Yes. Two blocks. I discard these off diagonal blocks. I only take these diagonal blocks and I sum them up. So I get, by summing them up, I get one 2 by 2 block. So that would be row B. Okay. Now, let's again check this definition that I wrote it here. So for this state, this product form, we already know that, or maybe yeah, we can verify that square of these matrices is equal to themselves. So you take row A or row B, its square will be equal to itself. So row A square will be equal to row A, and similarly for row B. So you can do that as an exercise using matrix multiplication rule, or maybe I can do that here quickly. Let's see. So now this is something to note, the structure, how to take which blocks and what operations are needed to compute these partial traces from the full density matrix. And this is not limited to 2-level systems. You can have a 2-level system coupled with a 10-level system, or a maybe 100-level system, and then you will have the same block structure, but then the size of the blocks will be according to those sizes of those Hilbert spaces. Okay, so you just multiply this row A with row A. So row A square will be like 1/4, and so first row, first column, it will be like 1 + 1 is equal to 2. First row, second column, 2, 2, 2. Okay, so in this case, row A square is equal to row A, and that's special for these kind of states that can be written in this product form. Okay, for entangled state, this doesn't hold. For entangled state, row A square will be different from row A, and due to that, if you take trace of row A and trace of row square A, then those will be simple numbers, and then trace of row square A will be smaller than 1. Okay, so trace of a density matrix is 1 because it's usually normalized, but trace of its square doesn't have to be 1. For product form where square is equal to A, its trace is the same, equal to 1. But for entangled systems, trace of this quantity is not equal to 1, it's less than 1. Okay, so that indicates that the system or subsystem is entangled with something else.
Sir,
Yes?
इस केस में रो A और रो B की like same ही matrices हमारे पास आए, same ही form बनी है, तो ये हमेशा ऐसा ही होगा?
No, so the question is that here we have row A and row B, they look exactly the same, and that's simply because the states look exactly the same. So if you take maybe minus sign here, I'm not sure, but I think it might give us a minus here and here.
Sir, अभी जो आपने states लिए वो आपने 1 2 लिए और like B में भी आपने 1 2 लिए, तो ऐसा हो सकता है कि हम 1 2 एक में ले लें और दूसरे में 1 0 ले लें?
No. These are two state systems. We label them as 1 and 2. You can label them as 0 and 1. We label them 1 and 2. So these are only two states. So if you add another state, then it would be a 3-level system.
Sir,
Yes.
the point is कि आप 1 और 2 जो ले रहे हैं वो दोनों states के लिए, चाहे वो psi A हो चाहे वो psi B हो, दोनों के लिए same ही रहनी चाहिए?
I'm putting a label A and B here, so it's very clear.
Sir, जो CAT के अंदर लिखा है ना 1 में, उसकी बात कर रही हूँ.
हाँ, लेकिन बाहर A और B अगर लिखा है तो क्लियर है कि इसका मतलब क्या है. ये 1 उसकी अपनी हिल्बर्ट स्पेस का 1 है, ठीक है. आप उसको डिफरेंट नाम देना चाहें, इसको A और B कह दें, उसको 1 और 2 कह दें, इसको 0 1 कह दें, उसको 10 और 20 कह दें.
तभी भी जब हम उसको मैट्रिक्स में लिखेंगे तो 1 1 1 1 ही लिखा जाएगा. मैं ये पूछने जा रही हूँ.
आप जो मर्जी नाम दें, नामों से कोई कुछ नहीं होता. तो ये वाला ये लें भाई, यहाँ पे भी लिख लें.
सर, मैं ये नहीं पूछ रही, मैं ये कह रही हूँ कि वो जो कॉलम में आपने 1 1 लिखा है ना, वो हमेशा 1 1 ही होगा या 1 0 या कुछ और भी हो सकता है?
ये नंबर
जी, ये
कॉलम, ये नंबर यहाँ से आए ना, अगर इन बेसिस में आप इसको लिखेंगे, so if you write this state This is a state in the Hilbert space. If you write it in some basis, it will become a column vector. If you write it in these bases, then coefficient of this will be here and coefficient of this will be here. So it's like written in 1 and 2 bases. So this number means coefficient of this cat and the other number means coefficient of this cat. Okay. So that's why it's 1 and 1. So it could have been an iota here or another phase factor, then that phase factor would appear here.
सर इसमें भी सोचना ज़्यादा आसान होगा ना कि आपके पास इलेक्ट्रॉन है तो वो स्पिन अप में या डाउन में हो सकता है तो 1 और 2 की जगह हम अप और डाउन अगर लिखें तो दूसरा इलेक्ट्रॉन भी अप और डाउन में ही हो सकता है वो जो 1 2 है वो तो सेम ही रहेंगे
हाँ हाँ
और
सेम हिल्बर्ट स्पेस
हाँ जी
मगर एक ग्रीन इलेक्ट्रॉन है, एक ब्लू इलेक्ट्रॉन, ये दोनों एक जैसे।
हाँ
इधर अप इज द फर्स्ट इलेक्ट्रॉन, डाउन इज द सेकंड।
सर इनडिस्टिंग्विशेबल इलेक्ट्रॉन
अलग अलग।
ऐसे से ये जो रॉ स्क्वायर लेस देन 1 आता है यही नेगेटिविटी है
नेगेटिविटी, हाँ आप उसको उससे रिलेट कर सकते हैं, आप एंट्रोपी से रिलेट कर सकते हैं, सारे वो जस्ट मेजर्स हैं, कैसे आप उसको देखेंगे। सब्र करें, मैं उसमें आने लगा हूँ
एक और चीज़
थोड़ी देर में।
ये सारा फॉर्मूलिज्म समझ आ गया लेकिन अगर मेरे पास मुझे नहीं पता कि मैं उस स्टेट को प्रोडक्ट की फॉर्म में लिख सकती हूँ या फिर इंटेग्रल की फॉर्म में और 2 इलेक्ट्रॉन है मेरे पास, अब मैं देखना चाह रही हूँ
तो इलेक्ट्रॉन का मीन 2 स्पिन हाफ,
हाँ जी 2
इलेक्ट्रॉन की अपनी अलग से कोई काइनेटिक एनर्जी ये वो कुछ नहीं है, जस्ट उनकी स्पिन की डायनामिक्स है, तो वो उसको फिर आप स्पिन नहीं बोलते हैं, उसको फिर इलेक्ट्रॉन नहीं बोलते यूजुअली, ठीक है, क्योंकि इलेक्ट्रॉन से कन्फ्यूजन होती है कि इलेक्ट्रॉन की अपनी भी कोई डायनामिक्स हो सकती है ना, तो वो जस्ट स्पिन हाफ बोले हैं उसको। लोकलाइज, so if you have an electron localized inside an atom, it's not going away, so it's a bound state, so it's always there, so basically it's a spin.
सर अब मुझे कैसे पता लगेगा कि उसको मैंने इस तरह से प्रोडक्ट फॉर्म में लिखना है कि उनके सिंगलेट में है, ट्रिपलेट में है या फिर इंटेंगल्ड में है।
सिंगलेट ट्रिपलेट की एग्जांपल्स आ जाएंगी उसमें, आई थिंक आपको ये क्लियर हो जाएगा, ठीक है। अभी जब इंटेंगल्ड की फॉर्म्स में कुछ लूँगा ना आ जाएगा।
ये हो तो डेंसिटी मैट्रिक्स ये होगा, अगर स्टेट कुछ और हो तो डेंसिटी मैट्रिक्स।
हाँ
सर ये पहले पता होगा हमें कि ये
हाँ हाँ हाँ
अगर ये तो वो इस he's not saying I know the state, he says if this is the state.
नहीं सर मैं फाइंड करना चाह रही हूँ कि 2 इलेक्ट्रॉन है तो क्या वो इंटेंगल्ड है या फिर नहीं
हो सकता है इंटेंगल्ड, हो सकता है ना हो।
अच्छा ये गेस
वो
मतलब पहले से
डिपेंड
खुद
करता है,
करेंगे
अब वो एक दूसरे के साथ कभी रिश्ता रखते थे कि ये अगर इधर है ये इधर है, इसको पता नहीं कि इधर कैसे पहुंचा, ना इसको पता, बस ये है। लेकिन अगर एक ही जगह से शुरू हुए होते तो फिर एंटेंगल्ड होते, लेकिन नॉर्मली दे विल नॉट बी।
तो इंटेंगल्ड कोई स्टेट होगी या नहीं होगी ये एक अलग क्वेश्चन है, और किसी सिस्टम को, इस तरह के कंपोजिट सिस्टम को आप इंटेंगल्ड स्टेट उसकी फॉर्म करना चाहते हैं, कैसे करेंगे वो एक अलग तरह की सी चीज़ है। तो सिंगलेट और ट्रिपलेट 2 स्पिन हाफ पार्टिकल्स की जब आप बनाते हैं तो वो अगर एनर्जी में डिफरेंट होंगे और वो खुद से वेल डिफाइंड मतलब स्टेट्स होंगे तो फिर उनकी जो फॉर्म है वो इंटेंगल्ड ही है। वो आप देखेंगे अभी इंटेंगल्ड की
क्योंकि
हमेशा का क्या हुआ, ये स्टेट है तो स्टेट यही है, ये स्टेट अगर इवाल्व होकर कुछ और होगी तो चीज़ें चेंज हो जाएंगी। अगर आप एक टाइम पे किसी एक स्टेट की बात करेंगे ना कि वो उस स्टेट का स्ट्रक्चर कैसे है, ठीक है, तो हमेशा का तो कुछ नहीं पता, बाद में वो चेंज हों क्या पता, वो तो अलग चीज़ है, अलग क्वेश्चन है। तो एक टाइम पे आपके पास एक कैट लिखा हुआ है कंपोजिट सिस्टम का 2 स्पिन हाफ का, आप उसका स्ट्रक्चर देख के भी बता सकते हैं, इनका सिंगलेट और ट्रिपलेट्स इंटेंगल्ड हैं वो मैं आपको स्ट्रक्चर देख के आप बता सकते हैं, लेकिन डेंसिटी मैट्रिसेस के थ्रू भी आप चीज़ें कर सकते हैं, ठीक है। तो यहाँ पर सिर्फ ये है कि आप एक स्टेट से स्टार्ट करें, डेंसिटी मैट्रिक्स हो आपके पास कंपोजिट सिस्टम का, तो रिड्यूस डेंसिटी मैट्रिक्स कैलकुलेट कैसे करेंगे और फिर उनका यूज़ क्या है वो इंटेंगलमेंट बता सकते हैं, ठीक है। और यूजुअली आपको रिड्यूस्ड चाहिए होते हैं, ठीक है, क्योंकि यूजुअली आपका जो सिस्टम है इट्स नॉट एन आइसोलेटेड सिस्टम, इट्स ऑलवेज इंटरेक्टिंग विद इट्स environment, for example, or maybe some other similar systems nearby. I mean, it depends. So your system cannot always be represented by a state like this. So it's usually density matrix, and that density matrix well, I'll talk about the mixed state and you'll know more about that
सर
then.
और जब हम reduced density matrix निकाल रहे हैं तो हम तो entanglement खत्म नहीं कर रहे उसमें से
इंटेंगलमेंट का फिलहाल समझें कोई जिक्र भी ना करें बेशक आप, ठीक है. इट्स जस्ट a way to represent state of a subsystem. So these reduced density matrices, they represent state of our subsystem. Doesn't matter it's entangled or not. Okay, so it can represent state when it's entangled, and it can represent its states when it's not entangled. I mean, doesn't matter. It's a general formalism. So the converse is not this is not true for these cats. So for cat of a subsystem, to represent state of that subsystem, that system has to be unentangled from everything else. Okay, so I mean, I'll talk about the mixed states, then maybe you'll get this point. Okay, so here we have one example, and we see that now let's take another example, and this time let's not form this state by a product, but write it directly in the Hilbert space of this composite system, and we will see that it cannot be written as a product. So your singlet and triplet look like this. So let's suppose there is another state. Let's use another symbol. So this is a AB. For this AB composite system, this composite system is isolated. It's not interacting with anything else. So we can always write its cat. So let's suppose its cat is like 1 by square root 2 times 1 and 1, or maybe 1 and 2, and then plus 2 and 1. That's all. So let's talk about this state. So it only has these two components. Now you cannot write it as this product. So if you take this one out, there is no 1, there is 2. If you take this 2, then there is no 2 here. So you cannot write it as a product. So it can be written as a sum of products, as it is already written over here. So this is a product 1 and 2. So this basically it means 1 and 2, and this means 2 and 1. But this state is a superposition of these two. Okay, so that's a valid state. It's perfectly valid for this composite system. There is no problem with that. But when you talk about a subsystem now, then things are getting a little strange. So you compute this density matrix for this. So let's call it rho AB, and this matrix now it's 1 1 1 2 2 1 2 2. So it's the middle two states, so 3 and 4. Okay, so in our previous notation, these two are 3 and 4. So it's 1 by 2, so it's 1 by 2 over here. So these are our 4 blocks, and this is 1 2 3 and 4. So these are 1 1 1 2. These are 2 and 3, not 3 and 4. 2 and 3. Okay, so this is what we wrote as 2 3. So this is 1 2 3 4 1 2 3 and 4. So this number, it gives us a number here. So with 1 by 2. Okay, so this is 1, this is 1, so it will be 1. Similarly, this will be 1 from here, and then this will always also be 1. Okay, everything else is 0 in this case. So I mean, you get this. So we have 1 2 3 4 4 states, 1 1 1 2 2 1 2 2. Here we don't have 1 1 and 2 2, so this is only second and third state in this list. So the density matrix will not have any matrix elements, they are 0, and it will have only non-zero elements over here. So 2 2 3 3 and 2 3 and 3 2. Okay, these are real, so these are these are all ones. You could put in a phase factor that would give a complex number here and then its conjugate here, but these will always be real, okay, because this gives us the probabilities for these states, so they are always real. So now it's very easy to compute density matrix of row A for A and B. So can you do that? For A, what we talk about is with this block structure, you take trace in every block, and those will give you these 4 numbers. So you take trace, there is a 1 here, so I put one half here, and then take trace, it's 1, take trace over here, it's 1. Now here is the strange part. You take trace over here, it's 0 0. Now you take trace, it's 0. Similarly here, it's 0. Row B is also the same, so you can compute that. It's symmetric in A and B, that also gives you the same. So this is basically 1/2 times identity matrix, okay. Now what you can do is you can compute this quantity rho A square, and this is an identity, so its square is identity, but this number is 1/2, so its square is 1/4. So now square of this will be like 1/4 times identity, and then now when you take its trace, it's 1/4 plus 1/4, it's 1/2. So instead of 1, it's 1/2. Similarly for this case. So now for row A, trace row square A will be 1/2, which is less than 1. That's something that was not there in this case. In this case, we obtained row square is equal to row A, okay, and trace would be equal to 1. But here it's less than 1, and this indicates that this system, this subsystem A, is entangled with something, okay. What something it's entangled with? Here, of course, we know that it's entangled with the other subsystem B, and similarly this trace of row B square says the same. That means this system is entangled. Of course, they have to be entangled with each other, okay. So this is a composite system where the subsystems are entangled with each other. In that example, they were not. In this, they are. So this is a very special case. And
I think it can never be less than half. This is
yes. So yes, that's right. Thanks. So this is called maximally entangled states. Okay. So when you have this structure, when you have this perfect correlation or anti-correlation, if you, so let me talk about that. So yes, it cannot be less than. So in this case, suppose you like to measure state of system A, subsystem A. It can be either 1 or 2, one of the 2 states. But what happens if you get 1? So if your measurement produces 1 for state A, that would mean something for B. So state would be projected. So I told you the postulates about measurement. So when you measure a system, state is projected onto the eigenstate corresponding to that measurement. So if you do measurement on this and somehow you get this, because whatever you measure, you obtain its eigenvalue and all that. So then in this state, when you project it onto this one, this is discarded, you only get this part, and this would mean that you get 2 for B, which means basically that you actually get 1A, 2B, this part, so 1, 2. So I'm writing it like this. So if your measurement projects your state onto state 1 of A, then automatically state 2 will be 2. So in this case, there is no superposition for state 2. There is no something like that. So if there were something like that, this number would be slightly higher. Okay, so if this is projected onto A and B is determined, there is no more, no space for any other state of B. It's determined, 100% determined. Then you would say that it's correlated, perfectly correlated. Okay, so these, if they are perfectly correlated, that means if you measure one, you know the other as well, then you get this half, then you get zeros over here. Otherwise you get some number over here as well, and that would increase this number above half. It can still be less than 1, but it would be greater than half, and it would still be an entangled state. The whole state would still be an entangled state, but the degree of entanglement would be slightly less. So this is maximally entangled state. Okay, now there is very interesting mapping, not in the mathematical sense, but correspondence, that if you have a system in the product state, if you have your composite system in the product state, so that its individual subsystems are not entangled, then the density matrix of your subsystem, it gives you this, and we call such states pure state, and this pure state refers to the state of subsystem. So the subsystem is in a pure state. But if your subsystem is entangled with something, so if the state of the system is such that your subsystems are entangled with each other, then the state of your subsystems will not satisfy this, will be something like this or maybe little higher. Then they will be called mixed states. So there is this terminology, pure and mixed. Okay, and I'll tell you what this mix means. So here this is related to subsystem, and this is your full system, full composite system. So if it's a product, then state of your subsystem will be pure, and if this is entangled, then state of your subsystem will be mixed. Okay, and the degree of mixing can tell you the degree of entanglement. Now there is interesting, there are many interesting things that you can do with this, you can compute eigenvalues of this and compute its entropy, and if it's 0, that would mean it's pure, otherwise it's mixed. You can also use the Bloch for a qubit, for a 2-level system. You can use this Bloch sphere representation, and there the length of your Bloch sphere will tell you about the degree of mixing or entanglement. So if your rho A, we can write any 2x2 matrix in this form. So this is your Bloch vector, and the length of this Bloch vector, if it's equal to 1, then your state is on the Bloch sphere, then it's pure. That means it's not entangled with anything in the universe. And if it's entangled, then it's less than 1, then your subsystem is in the mixed state. That means it's entangled with something else. Okay, so this terminology, so it relates to this pure and mixed relates to your subsystem usually. You can also talk about the purity of the full state, but if it's isolated, it's always pure. So I mean, it's not
So
useful.
if magnitude of A is equal to 0, that
Yeah.
means that
Maximally entangled.
maximally
Yes. So in this case, you can compute this and it will be equal to 0. So Bloch vector,
can be A.
yes. So it comes to 0. So it's at the center of your Bloch sphere. For this case, maximally entangled case.
Maximally
Mixed. Maximally entangled or maximally mixed. So when you,
pure is A equals 1. A is the
yes,
max,
yes,
maximally impure.
yes. So mixed refers to the state of subsystem, and entangled, for entanglement, of course, you need to have another subsystem. So it's either when you talk about both components or you talk about full system, that again means for both components. So this is a full system. So that's why I made this chart here. So these two terminologies, they relate, they are for the states of the full system, composite full system, and these two are for the subsystem, and they relate like this vertically. So if your full system is in the product state, your subsystem is in a pure state. If your full system is in the entangled state, your subsystem is in the mixed state, and the degree of mixing can be obtained, can be from this, or in the Bloch representation for two-level system, it's from the length of this Bloch vector. For a pure state, it's always on the sphere. Now you can see what happens if you have a two-level system and you couple it, I mean, with something in the universe, and suppose you started with a pure state. What would happen? Suppose it's interacting, then the dynamics will generate some entanglement over time, and then your Bloch vector will start getting inside the sphere, and if it gets maximally entangled, then it will go to 0. Okay, so you can use, there is a very good Python package, it's called Qtip. So you can use Qtip to see the dynamics of a two-level system on the Bloch sphere. So it has tools for visualization as well. So if you just see its example, you can, if you know about something about Python, then you can use the same scripts and generate evolution of the state on the Bloch sphere. Okay, how much time do I have? So do you have any questions?
सर स्टेट का नहीं समझ आया कि कैसे लिखेंगे, हमें कैसे पता लगेगा कि उसको इस तरह अलग करके लिखना है या फिर
आप यहाँ पे आई थिंक एज्यूम कर लें कि ये सारी चीज़ें पहले से पता होंगी हमें कि वो क्या है। ये पहले से नहीं पता, ये स्टेट लिखने के इक्वल ही चीज़ है, ठीक है। तो आप ये वाली चीज़ के सिस्टम इंटेंगल्ड है किसी दूसरे सिस्टम के साथ या नहीं, कहाँ से देखेंगे? आप उसके सिस्टम की स्टेट से देखेंगे, ठीक है। तो ये चीज़ पहले नहीं पता होगी स्टेट लिखने से भी पहले। तो आपको किसी सिस्टम की स्टेट पता हो तो वहाँ से ये चीज़ आप ऑब्टेन कर सकते हैं, लेकिन आप पहले से कुछ पता हो और वहाँ से सिस्टम की स्टेट लिखें, यूजुअली ऐसे नहीं करते आप, ठीक है। I have 1 minute, so let me tell you something about the spin, and it can be a good exercise. Maybe it will take about half an hour for you. So since I don't want to
Maybe you can tell us about the bell states, 4 of them.
oh yes, I thought about that, but yeah, the time is too late. So there are for 2 qubits, or 2 spin half, or 2 level systems. So yes, that's the natural thing. So if you have this should we keep using the same notation? Yeah, I guess. So we have the same notation for system A and B. Then we have these 4 states, which are 1 1 plus minus 2 2, and you normalize it and you obtain 1 by square root 2. So there are 2 these and there are 2 these. These are 4 states, 2 plus 2 4. These are called Bell state, and these are maximally entangled. Okay, and what's interesting about them is that they are maximally entangled. So if you make a measurement on first qubit, a 2-level system, you know the other, and that's the basis of this quantum teleportation and other stuff. Yeah, you want to me what kind of
These bell states also form a complete set.
yes.
In the
Yeah. So instead of using these 4 as bases, you can use these 4 Bell states because they are orthogonal and normalized as well. So they form the basis for this 2 qubit space, Hilbert space of this 2 qubit.
इसको पहले की तरह लिखते सुपरपोजिशन में, तब अगर हम फर्स्ट पे मेजरमेंट करते 1 अगर फॉर एग्जांपल, तब हमारे पास मैक्सिमली इंटेंगल्ड नहीं था वो, मतलब 1 भी हो सकता है 2 भी हो सकता है।
A B C D all 4 are non-zero. Yes.
तो अब ये कैसे पता लगा कि ये
हाँ, यहाँ पे आप इन 4 में से कोई भी स्टेट लें, when you make a measurement on first qubit, you know the second because it has this structure. So if you know the system is in this state, then I mean it has built in this structure is built in. But suppose you take a general case. So you have 1 1 plus 1 2 plus 2 1. Okay, I'm not normalizing them, divided by square root 3. Okay, so if you have this, now if you make measurement on first and you get 1, this would mean that the state is collapsed onto the first, but this first is over here and here as well, so this is discarded, but you still get this. That would mean that for 2 you get this 1 and this 2. Now you don't know which one state your B is in. It's in a superposition, so you don't know yet in this basis.
अच्छा यहाँ से वहाँ पर नहीं गए, वो अलग हो गया,
यहाँ से वहाँ
मतलब इस सुपरपोजिशन में से ये चीज़ नहीं बनाई, ये के मैक्सिमली इंटेंगल्ड वाली अलग करती है।
नहीं, इसमें सिर्फ 2 पॉसिबिलिटीज़ हैं, 2 सुपरपोजिशन है 2 स्टेट्स की, इन 2 स्टेट्स की इन बेसिस में। तो यहाँ पे बेसिस का भी एक है थोड़ा सा, लेकिन अब उतना ज़्यादा टाइम नहीं है डिस्कशन में, या अगले लेक्चर में मैं उसको थोड़ा सा मज़ीद एक्सप्लेन कर दूंगा, और उसका उसमें हाफ की भी चीज़ें उसमें आ सकती हैं, ठीक है, तो वो एक कंप्लीट चीज़ बन जाएगी। अभी मैं जो असाइनमेंट वो एक्सरसाइज कह रहा था वो भी स्पिन हाफ की थी, तो वो सारी चीज़ें एक साथ आ सकती हैं। तो यहाँ पर ये सिर्फ 2 हैं, अगर कोई तीसरी होती जिसमें 1 होता तो इस तरह की चीज़ होती, तो ये परफेक्टली कोरिलेटेड नहीं है उतनी, ठीक है। अगर आप 1 को मेजर करते हैं और ये मिलता है, 2 को मेजर करें अगर इसी बेसिस में, ठीक है, यानी कि सपोज करें ये स्पिन हाफ है, तो स्पिन हाफ में आप z, x, y और कोई और आर्बिट्रेरी डायरेक्शन ले सकते हैं क्वांटाइजेशन की डायरेक्शन के तौर पे, और स्पिन हाफ का कंपोनेंट अलॉन्ग दैट डायरेक्शन आप मेजर कर सकते हैं। आपको हमेशा उसकी आइगन वैल्यूज प्लस हाफ एंड माइनस हाफ ये वही मिलेंगी, उसी के करस्पॉन्डिंग स्टेट पे प्रोजेक्ट होगा सिस्टम की स्टेट, ठीक है। तो अगर आप इसको मेजर करते हैं तो आपको ये सुपरपोजिशन मिलती है, ठीक है। अब अगर आपको पता हो कि इसको मेजर करना है तो आप ये सिग्मा एक्स की आइगन स्टेट बनती है, ठीक है, ये ऐसे कर लें इसको। अगर आप खुद से मेजर ही इसको करें तो हमेशा यही मिलेगी, ठीक है। लेकिन वो इन्फॉर्मेशन फिर पहले से पता हो कि कौन सी मेजर करनी है, ठीक है। तो क्वांटम इन्फॉर्मेशन और कंप्यूटेशन में यूजुअली इसी तरह के प्रोटोकॉल्स हैं कि आपको क्या पता है क्या नहीं पता और कौन सी मेजर करनी है कौन सी नहीं करनी है। उसी की बेसिस पे ये जो इंटेंगलमेंट का स्ट्रक्चर है इसकी वजह से इन्फॉर्मेशन को आप प्रोसेस करते हैं, ठीक है। Any questions? Okay, then yeah, let me give you the exercise. So here's the exercise for spin half. So last time I used this and I did not tell you how to obtain this maybe. So instead of going into details of full theory of angular momentum, we can skip many things and only rely on one thing, that angular momentum or spin would generate a rotation. So these are generator of rotation. So just like time evolution, you have this, or maybe let's suppose around phi you want to make a rotation around z axis with by an angle phi. Then this is the operator for that. Okay, so in general for any direction you can do. So let's put unit vector n here. Okay, this is an operator in the spin space. That means this is an operator in the spin space. So this is rotation in the spin space. If you use the orbital angular momentum, then that would be a rotation in coordinate space. Okay, and that's very easy to derive actually. But we can rely on this, and we can start with another information, that for a quantum spin half, whenever you choose any axis for measurement of its components, you obtain either plus half or minus half. So plus h bar by 2 or minus h bar by 2 if you care about the dimensions. So suppose we take this z as a reference, then we have two possible outcomes for its measurement, either plus half or minus half, and we can label corresponding states as plus half or minus half, or maybe plus minus z, so that it's eigenstate of z as z. So this will be like h bar by 2. Okay, so with this information and this information, you can get as x and sy are their eigenstates and write them as polymetrics. So suppose you have a state, okay, here. So if you rotate it by pi by 2, then it will become a state of spin operator along x with eigenvalue plus half. Okay, so that means you take this plus z, you rotate it around phi, around y, so that means you do this, and phi is pi by 2, so it's pi by 2. Okay, so before going that I need sz. So if I write this sz in its own eigenbasis, I simply get this, which is polymetric sigma z, but yeah, let's call it. So we can have that. So you do this, and what you get is plus x, and Now you can use this to determine matrix elements of Sx and Sy. So that's a good exercise, I guess. So all you need is this rotation, this information in this or this form, and then you apply different rotations. Now what's good about this is that these eigenvectors represented in its own eigenbasis. So suppose this will be like 1 and 0, and the other will be like 0, 1. Now if you are in this xy plane, anywhere in this xy plane, and you look at the z, then the z is kind of a symmetric. So that would tell you that if you measure a component of your spin along any direction in this plane, you would get plus z and minus z with equal probability. That means for anything in this xy plane, so let's call it xy, it would be something like 1 1. Okay, there could be a phase vector here, so let's call it I theta or something. And now what you can do, you can pick one of this theta for your x and then make these rotations to get this, and then you can write your sigma, your operator for that in that basis as well. So I think I don't have that much time, so yes. So this is a good exercise if you like to do, and if you have anything to discuss, I'll be available.